thank the organizer for including me in this wonderful program. Today I want to talk about transfer of a passive scalar, and I will consider the advected flow to be confined to large scale only. So let me skip the outline and go straight to the problem. This equation is the equation governing the advection and diffusion of a scalar theta. The flow yield is incompressible. And for the next 30 minutes, we will have to live in Fourier space. The flow I consider will be confined within this ball of radius k sub d, right? So large scale. Anything beyond k sub d will be 0. Right? And the questions are these. Given a persistent source f, okay, this source will be injecting the variance into the system persistently, okay? And my flow is finite. What can we say about the scalar variance flux? The flux going across some large wave number k sub star, okay? And the corresponding spectrum at that wave number. Okay? This is a classical problem. Spectrum, transfer, and flux. Okay? Can we handle this problem rigorously? Okay. Some of you might know the answer already. Yes, we can. we can because this problem is very nice. It's a linear problem. And not only linear, but the flow is very nice. The flow is infinitely smooth. So that's why we can handle this rigorously. But actually, this problem is not so restrictive, even though I consider just smooth flow within a ball of k sub d. It's kind of general if you consider Bachelor problem 1959. Bachelor considered turbulent flow, but if we set the exponential decaying tail in Bachelor problem to 0, and we identify the viscous dissipation wave number k sub nu with the wave number k sub d that confine the flow within that ball, and identify the viscous convective range with this range here, the largest wave number supporting the flow, and the diffusive wave number, then the problem of Bachelor just reduced to this problem nicely. They are just identical within this approximation. Ignore the decaying tail of the turbulence flow. Okay? And what have we found for this problem? No new physics. But there are some new things. We found a clear and manageable picture of variance transfer in wave number space. The picture is very clear. You will see it in the next 2 slides. And we have got this constraint between the spectrum and the flux. Okay? Okay. This constraint is in terms of the velocity, right? The maximum velocity, the maximum wave number supporting the flow, and look at this Bachelor spectrum k-1. Right? So this is almost exactly the same as what George Bachelor had in 59, but here I don't have the dissipation of energy or viscosity, nothing like that in my setup. Okay? So in some sense, this is kind of general. Okay? It can be applied to 2D, 3D, 4D, whatever dimension we can imagine. It depends on the strength of the flow, the maximum wave number supporting the flow. Okay? This term is exactly the term in Bachelor formula, and this is k-1, of course, in George Bachelor formula as well. Okay? So the only difference is this denominator here. Okay. And the third point I got is that a generalization of this result to large-scale advection problems. Right? Any large-scale advection problems can have similar result with this, and including those in models of turbulence. Right? So I think the last point is kind of important because we work with models turbulence all the time. So it may be considered in a new result. Before showing you those results, I'd like to take you back in time for a brief history of this problem. I may not know very well about this history than many of you, but I try to give you some perspective anyway. The first people who considered this problem may be Obukov and Korsin in 49 and 51. And these two authors consider the regime where the viscosity and diffusivity are almost the same. They are more or less the same, comparable. And the result they found, just like in Komolov theory, came as 5/3 for the scalar spectrum, variance scalar spectrum. And this is for wave numbers smaller than the viscous dissipation wave number, which is the same as the diffusive wave number because viscosity and diffusivity are comparable. Okay? So in some sense, there's nothing new in the generalization from Komarov to this problem. Right? But Bachelor in 59 considered a different regime where the diffusivity wave number is much greater than the viscous wave number. So there is a wide viscous convective range between the energy dissipation and the scalar dissipation wave number. And in this regime, he found something totally different. It came in as one spectrum in that regime. And of course, in the other regime, the spectrum is supposed to be came in as 5/3. So if you combine this one with Obukov and Korsin theory, then you have came in as 5/3 down to the viscous dissipation scale, and then followed by this Bachelor spectrum. Okay. And again, I just draw your attention to the dependence on the energy dissipation here. So this problem is specifically designed or considered for Komarov turbulence, just confined to that particular case only. Okay? Without energy dissipation, without viscosity, then you just cannot have this formula. Okay? And for the next 49 years, many people consider this problem, and you can easily find 100 papers in the literature about this. I just listed here maybe 30 of them. I hope I don't miss some paper from the audience. Okay. Now let me give you more details about this problem. It's kind of more mathematics here. I specify the support of U, okay, within this ball, and I divide the scalar field into two parts. The small wave number part confined within this ball here, theta sub small, and the other components, the complement of that, will be denoted by theta sub larger. Okay. And here the flux from the ball, the inner ball, to the outside world. Okay. And if you multiply the advection equation here by theta sub larger and take the spatial average, we work with periodic domain, so everything is nice in this system. Right? You have the time range of change of this variance, the variance outside of that ball. This is the diffusion term. And on the right-hand side, you have the flux term. Right? The flux term here can be simplified a bit, right? Because U is incompressible. So you can write the flux term this way. Right? One component, the larger component, drop out from the radiant term here. Right? So far, everything is exact. Right? And this is the flux. This flux will give rise to variation in the variance, and also will fit the dissipation. Right? And we are concerned with this flux now. To make any calculation of that flux now, we go to Fourier space. The velocity field is expanded in Fourier series. Okay? Wave number k will be smaller than k sub d. Okay? For theta, we have full expansion. Okay? Incompressibility, and I ignore the reality condition for these two fields. Now the flux term in spectral form. Okay? You have one mode from this guy, the purple guy. Okay? One mode from the green one, this here. The gradient gives you a wave number from this guy, and this mode is from the affecting field, okay? Triple product, and we have to respect this triad condition. And look at this triad. We have 1k from the something outside of the big ball. Okay, this k is inside the big ball, and this k double prime is inside the smaller ball, the red ball. Okay, the triad will require this, because without this condition, this guy and this guy cannot connect with this guy. Okay? You will see it's a bit better on the next slide. Okay? So only wave number within this shell, the shell of radius 2k sub d, center at k sub star, will contribute to this flux term. Anything inside and outside of this shell will be drop out. So they are not in the picture. Yeah. This picture will show you clearly what I just said. Okay. If you have a mode from here and a mode from there, the distance between them will be greater than k sub d. They cannot connect. They cannot make a triad. So that's why I said they drop out. Okay. So only a mode from here and a mode from there may connect. A mode from here and a mode from there may connect. Right? So only wave number within this shell here will make a contribution to this flux term. Okay? And if I denote theta sub I to be the inner shell, starting from k sub star minus k sub d from here to k sub star, okay, and theta sub e is the exterior shell, starting from k sub star to k sub star plus kd. Then only these two guys will be present in my flux term. So in some sense, this is a very local transfer. Anything outside of this picture will not be in the flux term. Okay. And here is a remark I want to make on this transfer locality. When you take k sub star to infinity, then the ratio between the two wave numbers that involved in any triad will approach unity. Okay. So they are getting closer and closer in terms of this, because the ratio will be approaching 1. they are always within KD of each other, and when you take them both to infinity, then the ratio will be approaching 1. That's what I mean by highly local. Okay? In general, there are couplings for which this ratio remains strictly greater than unity in that limit, but those couplings are not present in this problem. They are not, because my flow is within that KD radius only. So this allows me to make very good estimate of the flux term. And here, just simple approximation. My flux term here, you remember on the last slide we had this triple product term, and if I want to approximate this, I just put absolute value on 3 of these, and after that I just pull one of them out, namely u, and in doing that I replace with the maximum velocity. Okay, in here I have this and that. Okay. And from here to here, just Cauchy-Schwarz inequality, and then from here, remember theta sub I is within the shell of radius k star and k star minus k sub d. Okay, so the maximum wave number in this guy is k sub star. Okay, so if I want to estimate this, I will replace this one with k sub star, the maximum wave number there, and just the variance of this component. Right? So from here to here is also straightforward from the picture that I showed. Right? From here to here is just the geometric average is smaller than this usual average, arithmetic average. Right? And I call this one the spectrum at wave number k sub star. Right? I think I already said what big U is. Okay. So this spectrum is the average variance over the shell of radius 2 k sub d, center at k sub star. And this is not much different from the usual spectrum that we have. And here you can see why it's not much different. Okay. This theta is apparently approximates the usual spectrum. And you can see from this, if you consider the Bachelor spectrum here came as 1, then by making substitution of that into here, then you get to this approximation. And when you take the ratio here to 0, that means you go further and further to infinity for your k here, then the whole thing here will reduce to exactly what we started with. Right? So the newly defined spectrum tends to the usual spectrum at high wave numbers. Okay, at least for power law scaling. For exponential scaling, it may be close, but will not approach. But for normal scaling like power law scaling, then the two spectra are not much different. Right? So we are working with this newly defined spectrum rather than with the usual one. Right? And that's it. After that definition, then from the result on the last 2 slides, I guess. Oh no. Where is it? Where did I get that? Oh yeah, here. Yeah. Okay, the flux is bounded from above by this. Okay, so I just rewrite this inequality for the spectrum. So the spectrum will be bounded from below. Okay, just rewrite that equation. I get this equation. Okay, so my spectrum will be bounded from below by that. Okay? And what does this one mean? This means that if I have a positive flux, whatever it is, a positive flux here, to ever smaller scale, then my variance must diverge. It's just trivial from this, even if my flux is diminishing, right? Even if I don't have constant flux, but my flux is getting smaller and smaller to zero, not faster than 1 over log k, then I must have this in order to support that diminishing flux. Okay. So given a persistent source, if I have persistent injection, then my variance will be diverging. Right? No question about it. It doesn't matter what dynamics I have. It doesn't matter whether I have a flux or not, because if I don't have a flux, then my injection will build up at the large scale, so the variance will diverge anyway. So in any case, I will have this limit if I take k bar to 0, if I take k sub k bar to infinity, or if I have no dissipation. If I consider no dissipation and I just continue put in my variance, then I will have blow up of the variance. Okay, one remark on that variance flux. It's totally different from Obukhov and Corsin variance cascade and the Komarov energy cascade, where we can imagine the inertial range have no energy or no variance in both picture, right? Because in their picture, k minus 5/3 will have nothing, no variance or no energy in there. Okay. A cascade in the present case, if realizable, would be far less dramatic. And I say leaking through a fully filled inertial range, because the inertial range has to be filled before I can see further cascade. So you can see the two pictures is fundamentally different for these cases. Okay, now I will try to generalize this result to Navier-Stokes equation. Okay. Here is the Navier-Stokes equation, and I will consider big U as a red U here, just like the red U that I had for the scalar case. Okay. And U prime is a complement of that, so my velocity view will be red U and U prime. So red U is supported by that bore with maximum wave number k sub d. Okay. And I will define V sub smaller, V sub larger, V sub I, V sub E, and big Vk exactly the same way as I define these guys. Okay. So this is equivalent to that one. So this is energy spectrum, right? The velocity spectrum. Right? And with this, I will carry the result for scalar to this case straightforwardly. Okay. Now look at the energy flux. Okay, my forcing F here. Okay. The energy flux will be given by this exactly, and everything will drop if I partition my velocity field into two components like this, the red one, and the U prime one will be anything from here to infinity. Right? So my affecting flow will be decomposed into two components. Okay, the flux due to U, okay, is exactly the same as the flux for my scalar. Okay? And this contributing term is due to the advection of the small scale. Right? Advection of smaller scale velocity here. Right? And from my scalar result, you can imagine what this one is. Right? This one will be diminishing if the energy spectrum is deeper than k-1, and in Komarov picture, we have k-minus factor too steep for this guy to make any significant contribution. So the entire flux in the classical theory is due to small scale advection. Okay? So in some sense, you can ignore completely the contribution of the large scale advection. So large scale advection like have nothing to do with the energy flux in the classical spectrum, because the spectrum is too steep for that. Right? And this has straightforward application to regularization model of turbulence. Okay? In many model of turbulence, we just consider large-scale advection. The advected field is the fully turbulent field. Okay, V is the full turbulent field, but U is just confined to large scale. Okay, we ignore the small tail of the velocity in the advecting velocity. Okay, by doing that, you get rid of all the small scale in your advecting flow, and then you just get this term alone for the flux. The term due to small scale advection you have already ignored. Right? And if you do that in your regularization model of turbulence, you will not see Kolmogorov cascade, because in order to have a cascade, you must have energy spectrum at least not steeper than k-1. Okay. Okay. So there is no direct cascade. I mean, no Kolmogorov cascade if you consider those type of models of turbulence. Okay, with that, I'd like to come to this concluding remarks. For a large-scale flow confined to wave number within this ball of radius k sub d, the transfer is only between wave number within k sub d of each other. Okay, if they are different more than this, then they do not make a triad. They do not couple. Right? And at high k, this highly local transfer is significant only if the scalar spectrum becomes no steeper than k-1. Okay, you must have k-1 or shallower in order to have a flux. Right? Only then could a non-zero variance flux to a bounded range is realizable. Otherwise, the spectrum just keep rising. Right? Okay, and in any case, if you have a flux or not, given a persistent source, the variance must diverge in the limit of zero diffusivity. And I'd like to take this opportunity to advertise another paper of mine. If the flows are not restricted to large scales, then the problem is more complicated, you can imagine, because we have all small scale in your advection term. The flux term will involve almost, so it's become unmanageable by my method here. But nevertheless, you can make an estimate of the flux if you make this assumption. If you assume that the velocity gradient is finite, then you can have very similar results. You can have k-1 spectrum, but the constraint for this case is weaker in the sense that you may have no variance at some point in your spectrum, followed by something significant as k-1 spectrum. But in the case I just showed you, that's not allowed. You must have continuous spectrum. There is no gap in between any points. Okay? But in this case, because you have non-local transfer, then any gap in between cannot be ruled out. So this is kind of problematic. I don't think we should have some gap in between the spectrum, but nevertheless cannot rule out that case. So they are very similar. This problem and the problem of large scale affection very similar, except for that paralogical case that I just cannot rule out. Okay, and for you, those of you who are interested in this, you can check it in physics of fluid. Okay, thank you for your attention.
Any questions?
Is there any link between this work, and there's been a lot of work done on well posedness of transport equations, and recently the theory has been extended to transport by BV velocity fields, and I've shown that's well posed. I'm wondering if under those conditions you could show that your problem was well posed. That would be more general than what you've just shown.
If you confine the velocity field to that board, and then the problem is well posed.
That's not actually a spectral restriction, that's a restriction. And that actually allows you discontinuity, but it doesn't allow you indefinite oscillations. So under those conditions you can prove the transport equation can be solved. It wasn't when you're solving more than the transport equation, you have a diffusion and a forcing term. The transport equation, which then with the scale interactions can be solved, and I think we might be able to do the rest of the problem.
I don't understand exactly what your question is, but if you have finite diffusivity and your velocity field is nice, doesn't have to be confined within that radius. If I have nice velocity, smooth velocity, then the diffusion problem is well.
You might be able to relax yours. You might be able to have a slightly less nice velocity field and still solve the problem. I can talk afterwards.
Oh, we will discuss about this later.
The other found information about spectra I know of was I believe some years ago at least when Gibson's bound on the coefficient of k minus 1, which the closures, for example, direct interactions, such things proposed, had difficulty matching. Did you come across that in any way?
You mean the coefficient between k minus 1?
The coefficient k minus 1, he showed in a rigorous way, he claimed that there was a certain upper and lower bound.
My coefficient here depends on the flux and the maximum velocity field and the maximum wave number supporting the velocity field.
Maybe different.
It's rigorous. I don't see any coefficient like that in the literature. I don't think. Modular coefficient depends on viscosity, depends on dissipation of energy. This coefficient is completely independent of any theory. So you can just describe your velocity field, okay, and then there, well, you don't need to say, okay, my affecting flow is common of affecting flows or any other flows, like 2D, 3D, or 4D flows. 4D flows may be totally different from 3D flows. Nevertheless, the result will apply. Okay. So it doesn't depend on any theory.